All right, let's look at noble gas configurations and how you'd come up with a noble gas configuration for an element, or maybe even an ion for that matter. We have to consider, for example, a long electron configuration such as this example for cesium. So we should see that that is quite long, and that's a pain to write out all 55 electrons. So there's a shorter way to do it. And the shorter way is to take advantage of the fact that we can reference nearby noble gases. Because we understand, like if we look at a noble gas, let's take the nearest one to cesium, and we need a periodic table for that. There's cesium, and there is xenon, the nearest noble gas. Or at least the last noble gas that comes before xenon. We're going to ignore, even for like iodine, we would actually be looking at krypton and not xenon. So if we're looking at iodine, you look at the noble gas that comes before. Look at bromine, look at the noble gas that comes before. So no matter what element we're going to do this for, you look at the noble gas that came before it, not after it. So for cesium, the last noble gas that came before it was xenon. So we should understand that the electron configuration for xenon and cesium is essentially identical, with the exception of cesium would just have one electron more because it's number 55, and xenon's 54, which means this would be the only difference. It has this, whereas xenon does not have this. So we're going to say is for cesium, it has the exact same electron configuration as xenon. The only difference is that in addition to xenon, it has this 1s, or sorry, it has this 6s1. So 1, 2, 3, 4, 5, 6. Yes, 6s1. And that way, instead of writing out a big long thing like this, we can instead write out a little short thing like this. And it works for anything. For carbon, for example, even for short ones. Let's do carbon. For carbon, the last noble gas for carbon was helium, so it'd be helium. And then what came after helium? 2s2, 2p2. That's it. That's the noble gas configuration for carbon. Even very large elements. Let's do lead. Okay, a giant thing like lead. If you want to do lead, that's 1s2, 2s2, 2p6, 3s2, 3p6, 4, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and so on. It goes on. Let's shorten that. So the last noble gas before lead is xenon. And then we just basically, that means, okay, xenon, and then continue from there. So what's after xenon? 6s2. So these are 6s2. Okay, as you cross over this, which is the 4f14. All of these 4f14s are crammed into this little space. So 4f14. And then after you cross over the 4f14, you get the 5d10. And then once you cross over the 5d10, you've got the 6p1, 6p2. Oops, it's off screen. There we go. 6p1, 6p2. 6p2. And that's it. That's the noble gas configuration for lead. Now, what if I get a little tricky and I'm like, all right, give me a noble gas configuration for a noble gas. Let's do Kr. That's krypton. Right there. Nope, sorry, you don't get to just put krypton in brackets and call it good. You have to do the previous, same rules. Previous noble gas, that's argon. Right, we see previous noble gas for krypton is argon. And then what came after argon? Let's see. All right, let me make sure you can see the whole process of what I'm doing. Let's make sure you, the viewer, can see how I'm getting this. So for krypton, last noble gas was argon. So argon, then 4s2, 3d10, 4p6. So that's how you handle it for a noble gas. And suppose I want to throw out maybe a ion. Let's do fluoride ion. So what I will do for this is I will, same as before, I will start with doing the noble gas configuration for fluorine first. So I will first do fluorine. Previous noble gas is helium. And that's helium followed by 2s2, 2p5. Now remember fluorine, that's you add 1 electron, which means you add 1 electron here. So it'd be almost the same configuration except 2s2, 2p, 1 more, 6. And this would be your answer for the fluoride, and this would be merely like your work. It's recommended to do this first and then add however many or subtract however many electrons instead of just doing straight this, only this, because people make mistakes here. Whereas if you do it for the neutral element and then add or subtract the right number of electrons, you're less likely to make a mistake. All right, that should give a nice overview of the various different ways to handle abbreviated electron configurations. For practice, I would suggest looking at this on the notes, and I'll put it up right here for you to see too. So here's some practice examples. I would suggest pause the video here, work out the ones you want to work out, and in a moment I'll reveal the answers, which are these. All right, there we go. Happy studies.